So now we will recall what we did in the exercises. So we take again phi x, phi of r equals 1 by 2 pi log r if n equals 2 and is equal to minus 1 by n minus 2 alpha n r to the 2 minus n if n is greater or equal to 3, alpha n equals surface measure of the unit ball in Rn. And recall, this is the fundamental solution of the Laplacian. So if you have that minus Laplacian u or equal to f, okay, so then you have that u of x equal to and u equal to g on the boundary. Then we proved that u of x, u is in C2 of omega intersection C of omega bar. This would do actually. So then u of x is equal to minus integral f. Okay. So I will write it differently now. So it will give you delta u g of xy dy plus integral on gamma u of y dg by d nu of g of xy d sigma y. Okay, so this we already saw the representation formula. Okay, so then we now look at x in omega and we take epsilon such that rho such that bx rho is contained in omega. Okay, and we apply this formula to bx rho. Now what is the Green's function in bx rho? So if you have a ball, what was the how did we define? We defined phi super x of y, delta phi super x of y equal to 0, y in omega, and phi super x of y is phi of mod x minus y. Okay. Now phi of mod x minus y, if you are in bx rho, this is nothing but phi of rho. Okay. So this is just phi of rho. Okay, and the Green's function is equals phi of mod x minus y minus phi of rho. Okay, so if omega equals bx rho, y in bx rho. Okay, we are going to take okay the x naught rho if you like. Okay, x naught for the fixed point x naught. So if x naught is in omega, then you take bx naught rho is this function here, and therefore you will get that u of x naught equal to integral b of x naught rho phi of mod x minus y minus phi of rho dy plus integral u of y, and then what is d by dxn? So we have to d by d nu is nothing but d by dr, because you have a ball and then r is the normal direction. So d by d nu is nothing but d by dr, and so if you put it there, so then you get mod y minus x naught equal to rho, and if you d by dr, if you compute, it is just 1 by alpha n rho to the n minus 1. d phi by dr equals 1 by alpha n rho to the n minus 1. That is straight away immediate from this the formula for n bigger than or equal to 3. For n equals 2, log r will give you 1 by r, that is 1 by 2 pi r. 2 pi is alpha 2 because the perimeter of the circle, and rho to the 2 minus 1 is nothing but the rho itself. Okay, fine. So you get this, and now We also okay, delta u. You get this formula. Okay, so now assume that delta u equal to 0 in omega. Then the first term will disappear, and therefore for every x in omega we have u of x is equal to 1 by alpha n rho to the n minus 1 integral y u of y d sigma y mod y minus x equal to rho. Okay, so this is called the Gauss law of the arithmetic mean. For a harmonic function. Okay. So, the harmonic function satisfies the following property: any value at any point in the domain is the average of the value on any ball surrounding it, on the sphere surrounding it. Now, you also from this you can get another mean value theorem. So, these two are called mean value theorems, namely if you take, this is true for any radius. Okay, so this, as long as b of xr is contained in the domain omega, this is true, and therefore now if you take integral over b of x rho uy dy, this is equal to, I write it in polar coordinates, it is equal to 0 to rho dr integral mod y minus x equal to r uy d sigma y. So, I have integrate over every r and then I integrate over rho. This is just polar coordinates, but now this is equal to, because of the mean value property, the inner integral is nothing but alpha n ux will come out, it is a constant, integral 0 to rho power n minus 1 r power n minus 1 dr by dagger. And therefore, that is equal to alpha n, so by n ux rho power n, okay, and therefore this tells you that ux is the, but alpha n by n is nothing but omega n volume of unit ball and therefore ux is equal to 1 by omega n rho power n integral bx rho u of y dy. So, this is the second mean value theorem. So, first one says, so double dagger, the first one says that u is the average if you take any sphere of radius rho around the point, and this tells you this is the average of any ball of radius rho taken around the point. So, for a harmonic function, this is a very nice property which you have here. Conversely, if u belong to C2 omega intersection C of omega bar satisfies mean value property namely dagger, for every ball bx rho contained in omega, then delta u is 0 in omega. For if delta u is not equal to 0, then without loss of generality we can assume that there exists a Bx rho contained in omega such that delta u is say positive, for instance, for example, or negative in Bx rho, because it's a delta is a continuous function. The function is C2 and therefore second derivatives are continuous. So if it is positive at one point, since it is not 0, then it will be positive in a small neighborhood. If it's negative, you can take it to be negative also. It doesn't matter whether you are taking positive or negative. Now then it follows from this equation, call this triple star if you like. Observe phi is monotonic increasing. Okay, phi is a monotonic function. This function is monotonic increasing, as you can readily verify, and therefore if you look at triple star here, if delta u in that small ball is strictly positive, now phi x minus y minus phi rho will be negative. So this whole integral is going to be negative, and therefore you have triple star implies that u of x is strictly less than 1 by alpha n rho to the n minus 1 integral mod y minus x equal to rho u of y d sigma y, which is a contradiction because we know that the mean value property holds in every ball, and therefore you have that this is the function is in fact harmonic. Okay, so we have a definition at this point. You say that u in C of omega bar, okay, is said to be sub-harmonic respectively, sub-harmonic if for every Bx rho contained in omega we have Ux is less than or equal to 1 by alpha n rho power n minus 1 integral mod y minus x equal to rho of u of y d sigma y. Okay. So it will be super harmonic if you have greater than or equal to. Okay, so this is the condition. Okay, so if you have u in C2 omega intersection C of omega bar, then it is sub-harmonic if and only if delta u is greater than or equal to 0 in omega, and super-harmonic if and only if delta u is less than or equal to 0 in omega. It immediately follows from the definition. Okay. So now we have an important theorem. This is called the strong maximum principle. So omega in Rn, bounded, connected, open set. U in C2 of omega intersection C of omega bar. Let delta u be less than or equal to 0 in omega. So, it is a super harmonic function. Then either u equals a constant in omega, implies Laplacian u equal to 0, or u of x will be strictly bigger than infimum u over gamma for every x in omega. So, previously in the weak maximum principle, we saw that ux is greater than or equal to the infimum, because if f is Laplacian u equals f, Laplacian u is less than or equal to 0, so minus Laplacian u is greater or equal to 0. So, if f is greater or equal to 0, we saw that ux is greater or equal to infimum of u x in omega. Now, we say that if it is a connected open set, then either you will have that, and u is strictly, the infimum is attained only on the boundary, it cannot be attained in the interior of the domain for a connected open set. Okay, so proof. So, let m equals inf over gamma of u. Over omegas. So, you write omega 1 equals set of all x in omega such that ux equal to m, and omega 2 equals set of all x in omega such that ux is greater than m. So, u is continuous implies omega 2 is open. So, let x belong to omega 1, and you then have a bx rho contained in omega. Then delta u is less than or equal to 0, so super harmonic, and therefore you have that 0 is greater than or equal to integral mod y minus x equal to rho u of y d sigma y minus alpha n rho to the n minus 1 u of x, because u of x will be bigger than the average. So, average minus u of x is less than or equal to 0, but that is equal to, now this u of x is a constant, u of x is equal to u of x equal to m, okay, because x is in omega 1. So, this is equal to m, and therefore, this is equal to integral mod y minus x equal to rho of uy minus m d sigma y. Now, this integrand is greater than or equal to 0 because m is the infimum, and therefore, this is greater than or equal to 0. So, this implies that integral mod y minus x equal to rho of uy d sigma y equal to 0, minus m d sigma y equal to 0, and since the integrand is non-negative, this implies that uy equal to m for all mod x minus y equal to rho. So, same is true for all rho dash 0 less than rho dash less than or equal to rho, and that means for all bx x, so for all y in bx rho, we have ux equals m, and this implies that omega 1 is open. So, omega 1 intersection omega 2 is disjoint, and omega 1 union omega 2 is the whole space, and therefore, omega is connected. So, one of them has to be empty. and that completes the proof, because if omega 1 is empty, then omega equals omega 2. So, ux is strictly bigger than m, and that is precisely what we are showing here. That is, namely, the infimum has to occur only on the boundary, it cannot happen in the domain, and if otherwise ux omega is equal to m, that will be whole of omega. So, it will be equal to a constant. So, that proves the theorem. Okay. So, if remark again, strong maximum principle also available for sigma ij equals 1 to n d by dxj dxi of aij d by dxj plus sigma I equals 1 to n ai d by dxi plus a naught, where a naught is greater or equal to 0 and uniformly elliptic, the IAIJs. Okay. So, if this is true, then this is a theorem of half, theorem of half. Okay. And you can see proof either in Protter, Weinberger or Gilbert and Trudinger. Finally, corollary. So, u in C2 of omega intersection C of omega bar minus Laplacian u equals f greater or equal to 0 in omega, u equal to 0 on gamma implies either u is identically 0, this will imply that f equal to 0, or u is strictly bigger than 0 in omega, because the infimum can be attained only on the boundary. Okay. And therefore, this is a very nice and useful result to know. So, this is just a corollary of the strong maximum principle. Okay. So, with this we will wind up the maximum principles.